right, happy Wednesday morning, folks. It's been a busy beginning of the week, but I should be able to post exam 3 materials right after class today. So I started getting some stuff up and getting caught up on posting some of the videos and things, but I had to pause for some meetings and things I had yesterday, so. All right, so we've been talking about molecular structure using our knowledge of electrons and atoms and Lewis structures to then determine molecular shapes. Okay, so if you recall, right, we use this theory called VS-EPR, where the idea is that the positions of the nuclei, okay, so what we're calling shape in a molecule is really where the atomic nuclei are positioned with respect to one another in space, okay. Those are going to be determined, okay, by the fact that electrons in bonds and lone pairs want to be as far apart from one another as possible. Okay. So we looked at a few of these geometries, and where we wound up last class was by talking about sort of the impact of lone pairs. Okay, so if we have 4 things attached to our atom, our central atom, like we do in methane, we get what's called tetrahedral geometry, right? We've got one atom at each corner of a tetrahedron, okay, and the central atom in the center of that tetrahedron. And the angles of the bonds, so the bond angles, are 109.5 degrees, which is ideal what we call tetrahedral geometry. Okay. If we look at examples where we still have 4 things attached to our central atom, but some of those things now become lone pairs, okay, we start, okay, with the tetrahedral geometry, but because these lone pair electrons, okay, don't have another nucleus to be attracted to, their position in space is more diffuse, okay, so they're kind of spread out a little bit more than the electrons would be in this bond, okay, and so they can push on the other bonds a little bit more. And so what you see is when you have one lone pair, okay, and then 3 bonding pairs, that bond angle gets a little bit smaller, okay, it goes down to 107.5. And then in the water molecule, we actually have 2 lone pairs and 2 bonding pairs. And so what you see is that the angle in the water molecule, okay, is the smallest of the 3, okay. So all of these, okay, we would say have tetrahedral structural pair geometry or electron pair geometry, okay, but the molecular geometry is going to be slightly different due to the fact that we have some lone pairs and they have a slightly different influence on the other electrons than a bonding pair does. All right, so that's how lone pairs affect things, okay? So let's look at the geometries we get when we have 5 structural pairs. So we've got 5 things attached to our central atom. Okay, so in this case, okay, 3 of those things that are attached, okay, are going to be essentially in the same plane as the central atom. So we get that kind of that triangle with the central atom in the center, and then we have one atom above the plane and one atom below the plane. Okay, so those would be these atoms up on top and the bottom. Okay, so instead of having just one bond angle for everything that's attached to our central atom, we've got 2 different angles. Okay, so this is called trigonal bipyramidal geometry, or a trigonal bipyramid, okay? because, again, we've got the plane, and that's a triangle, and then we have a point above, so you could make a pyramid shape there, and a point below, and you can make a pyramid that goes below. All right. Now, when we add lone pairs to this, okay, you're essentially keeping the same geometry, the same kind of arrangement in space, okay, but you're going to be losing one thing. So imagine, in this case, when we have the lone pair, let's say we're going to just imagine that atom not there. Now it's a lone pair, okay, and what's the shape you get? The shape you get is called a seesaw. So this doesn't look much like a seesaw, but if we looked at it on an angle, okay, what you'd see is you'd have your central atom here, and then you'd have sort of two atoms going down and two off to the side. So it kind of really does look like a seesaw, okay? All right, then again, if we have another lone pair, okay, then imagine that, that one's not there, okay? And now what we get is a T shape, okay? And so in all these cases, okay, these angles that are in these molecules with lone pairs are going to be a little smaller than the 90 and the 120 that you see in when you don't have lone pairs, okay? And then finally, if you have 3 lone pairs on your central atom, you get the linear geometry, okay? And so these are the geometries that, are in the table that I gave you, okay? Now, when we have 2 different types of atoms in a structure, so when I mean 2 different types, what I mean is, so we have one type here, okay, in the trigonal bipyramid where we have them in plane with the central atom, and then we have ones that are above and ones that are below, okay? And so when we are trying to refer to these, as chemists, okay, we give them special names, okay? So the names that we give to them, tell us whether they're in plane with the central atom or not, okay? So things that are in plane with the central atom, okay, these are called the equatorial groups. So they can be atoms or groups, okay? These are the in-plane ones. And then the ones that are above or below are called axial. Okay, so we'll give those a different color. So they're on the long axis with the central atom, okay? And this gets used a lot in organic chemistry when we talk about the conformation of sugar molecules, okay? Basically, you get these ring shapes, okay? And the ring has a plane to it, although it's a little bit bent. And some of the groups will be some of the things pointing off of your sugar molecule will be in the plane of the ring, and some will be above or below, okay? And so we use those terms equatorial and axial. They come up again and again when we talk about molecular structure. Okay. All right, so getting to our kind of biggest structure in VSEPR theory, that's the octahedral geometry. So that's when you have 6 structural pairs, okay, so 6 things attached to your central atom. And so just like when we had the trigonal bipyramid geometry, in octahedral geometry, you have things that are in plane with your central atom. But in this case, those 4 atoms make a square, okay? And then you've got one above and one below. So again, this is more like the pyramid shape of Giza, okay? Where you have one above and then the other one down below, okay? But we call it octahedral because we've got 1, 2, 3, 4 corners of our square, okay? And And we have essentially two pyramids with a four-cornered base. All right, so when we have lone pairs, okay, we're going to be losing the axial things, okay? And so we'll keep so here we have just a plain square pyramid, right? Because we've lost the bottom pyramid, and we just have the top pyramid. So for this one, we've got the two pyramids, right? That's very bad art on my part, but all right. And then when we have a second lone pair, we just get square planar geometry, okay? All right. So, we can have molecules that look like they have the same number of things attached, right? So if we look at CH4, okay, that's methane. We're going to be coming back to this molecule over and over and over again, right? But if you look at your Lewis structure, right, the carbon doesn't have any lone pairs on it, right? And so you have what you call, this is tetrahedral, right? But if we look at XeF4, so xenon fluoride, what we have, okay, is because the xenon has these two lone pairs, okay, if we look, it's down lower below the third row, so it can have that expanded valence, right? And so it's got these extra electrons, and those are going to give it the square planar geometry, because having one above and one below is going to take, if we go back to our tetrahedral geometry here, okay, it's going to take these the groups in these position, or the atoms in those position, and it's just kind of push them flat, because there's something on either side pushing towards them. There's one lone pair above and one below. All right, so that's kind of the tour of our possible geometries. And we've talked about this before, how when we're drawing things on paper in 2 dimensions, we would like to be able to relay some 3-dimensional information. And so we use what's called wedge and dash notation. So what you see, again, is if there's a line, so any of these lines in blue, you could imagine that all these atoms and these bonds are just lying in the plane of the screen, okay? But if we have a solid wedge, okay, it's coming out towards us. So these guys are coming out towards us. And if you look, that is representing this atom right here, okay, in the ball and stick model, okay? And then our dashed wedge is the one that's going to be projecting behind the screen, okay? So this one is kind of shaded to look like it's going away from you, okay? All right, so let's try drawing this molecule right here in wedge and dash notation, okay? So, all right, so we've got a carbon here, okay? And what we're going to do is we're going to call this hydrogen, this carbon, and that oxygen as all being in one plane with one another, okay? So I'm going to have my hydrogen, my other carbon, my oxygen. All right, this hydrogen right here, we can also draw as in the plane. Okay. How about this oxygen that's double bonded? Does that look like it's in the same plane as those atoms? Looks like it to me. So we'll draw that up here. Right. So the only ones we have to worry about are these hydrogens right here, okay? So one of them is going to be coming towards us, right? That's this one right here. So that one we would draw with our solid wedge. And then the one that's going away from us, that's this one right here, we're going to draw with the dashed wedge. All right, and so that will tell us that, this hydrogen is, coming towards you in space, and this one's going away. All right. So the next thing we're going to do, okay, is we are going to take now our knowledge of molecular structure from VSEPR theory, okay? We're going to take our understanding of atoms and electronegativity and our understanding of bonds being polar or nonpolar, and we're going to use that to predict physical properties of molecules. And the physical property that we're going to predict is molecular polarity. Okay? That's going to affect directly all of these things here: vapor pressure, solubility, boiling and melting points. Okay? So solubility. Okay, you're going to hear this phrase probably. If you haven't heard it, that is not what I wanted. I wanted that. If you've heard it before, or you will hear it again if you haven't heard it before, the term like dissolves like. Okay, so things will be soluble, okay, in materials that have the same type of polarity as them. So solubility means the ability of two substances to mix, okay? So this is the ability of substances to mix. And again, we use this phrase like dissolves like, which means that two substances will mix well if they have similar polarities. So nonpolar is soluble in nonpolar, and polar mixes with polar. That's what that means. So we have to be able to figure out, okay, whether the molecule is polar or nonpolar. So, and a quick example of this solubility is, my favorite one, salad dressing, right? You've got oil and you've got vinegar usually, okay? And if you try to make salad dressing at home, or if you go to Tino's and you get a salad and they give you the little thing of dressing, you'll have the oil floating on top of the vinegar, right? Well, vinegar is a water-based solution. That's polar. The oil is nonpolar, and the two things don't mix, okay? Now, when you go to the grocery store and you buy salad dressing, you don't often see a separation between the oil and the water, and that's because they put things like emulsifiers in them. So if you make salad dressing at home, one of the things you can do is you put a little teaspoon of mustard or whatever in with your oil and vinegar, and then when you mix it, there are molecules in mustard that have both a polar end and a nonpolar end, so they can make the oil and the vinegar mix with one another, even though they have different polarities. Okay. All right. So, what do we need for a molecule to be polar? Okay. So, to be polar, a molecule must, first and foremost, have polar bonds, okay? So it must contain polar bonds. And the second thing, okay, because not all molecules that have polar bonds are polar. Second thing is that the polar bonds must be arranged so there's an uneven distribution of charge in the molecule. So there is an uneven distribution of charge. And this is in the molecule as a whole, okay? All right. Whoops. There we go. Okay. All right, so here we have two examples, okay, of chemical bonds, right? We've got fluorine with fluorine and hydrogen with fluorine, okay? So fluorine and fluorine, this is our table of electronegativities. Negativity. And again, that is a measure of the affinity that an atom has for electrons in a bond. Okay, so if we look at fluorine is 4. So when you have two fluorines together, they have the same electronegativity. Both sides of the bond have the same affinity for those electrons. So this is what we would call a nonpolar bond. Then when we look at the hydrogen, right, hydrogen has an electronegativity of 2.1. Fluorine has an electronegativity of 4.0. Okay, so this is what we would call a polar bond. And we would say that the electrons, right, distribute themselves unevenly between the two atoms. So this is, in essence, the fluorine gets more of the electron's time. Doesn't mean that the electrons in the bond don't go visiting the hydrogen nucleus sometimes, okay, but they spend more of their time near the fluorine. So that leaves the hydrogen with what we call a partial positive charge. And your fluorine with a partial negative charge. So anytime you see those little lowercase deltas, okay, that means partial charge, okay, and partial charge means if I were to look at the charges on these atoms, it wouldn't be +1, -1, it would be something like plus 0.8 minus 0.2 or something like that, okay? So it's something that's not an integer number. It's a fraction of a charge. All right, so we've got these two molecules, okay? One has a single nonpolar bond. The other has a single polar bond, okay? So in terms of, the molecules themselves, okay, we could say that this molecule is nonpolar. Oops. And this is a polar molecule. But it's not always that simple. Sometimes we have to sometimes we have more atoms and we have to actually look at what the geometry of the thing is. So, a general procedure for determining molecular polarity, okay, so remember it's important that we're talking about the molecule as a whole, okay, is to kind of follow the basic steps, right? We got to draw a Lewis structure so that we know what kind of bonds we have. Do we have lone pairs, okay? And then we're going to determine the shape, okay? So determining the shape, again, is consider structural pairs and lone pairs, and use the chart to figure out what kind of shape you have, where things are going, okay? And then, okay, you're going to use the shape of your molecule. Whoops. First, you got to figure out if you have polar bonds, okay? So if your bonds are all nonpolar, then your molecule is going to be nonpolar and you're good to go. But if you have a polar bond, okay, then you have to draw in what we call bond dipoles. So let's go back to our previous example of the hydrogen and the fluorine, and we're going to draw the bond dipole here, okay? So a bond dipole, okay, is an arrow that we draw, okay? Well, it's an actual physical measurement of an electric field, okay? But we use an arrow with a plus on one end to represent the bond dipole. So bond dipole, this points to the negative end, and we put a plus sign on the positive end, okay? And recall, we mentioned this before in class, the length is going to tell you something about the magnitude of the unequal distribution of charge. So if we have a lot of charge at one end, okay, and a little bit at a little bit at the other, it's going to be a long dipole. If the atom's electronegativity is more similar, then you would have a shorter bond dipole. So here we have, a very big difference between our two atoms. So we draw the bond dipole like that. Now let's say we're talking about a hydrogen and a nitrogen. Okay, so let's just make this here, okay? This is still going to be the positively charged end. This is still going to be the negatively charged end, okay? But the electronegativity of nitrogen is a whole point on the scale lower than fluorine, okay? So the bond dipole for this, okay, is going to be smaller. Okay, there's going to be less of a separation of charge, which means that if I'm keeping track of the time my bonding electrons spend around the hydrogen, okay, in this bond down here, the hydrogen is going to see more of the electron's time than in this bond up here, okay? So what it means is there's going to be a much smaller difference between the magnitude of these charges than there is between those. Okay. All right. So we have to consider shape in our considerings. Okay. So here we have a molecule BF3. Okay. So we've got three things attached to it, okay? And we've got fluorines at each end of the bond, okay? All right, so the fluorine, okay, is our most electronegative element, 4.0, okay? So I'm just going to put my electronegativities here. All right, and then for the boron, it's 2.0. All right, so for this molecule, okay, I've got three things attached to my central atom. So if we go all the way back to the chart, okay. Here we are in BF3. Happens to be one of our examples for when you have three things attached. Our geometry is trigonal planar, okay? So now let's go back. All right, so we've got trigonal planar geometry. So again, if I were to draw these atoms, okay, everything would fall in the same plane, and our three fluorine atoms are going to be at the corners of a triangle. All right, so our boron is in the middle, and we know that these are going to be polar bonds, okay? They are going to be polarized, okay, in the direction of the fluorine, right? So I'm going to draw my bond dipoles. and they're all pointing towards the fluorine. Okay. So the question I have to ask, okay, is this a polar molecule or not? Okay, so imagine, okay, that you've got people, somebody in the center, okay, and they're holding on to 3 ropes. And there are people on each corner of a triangle with the other end of the rope, and they're all pulling with the same force, okay? Because we have the same atom in each of those positions, okay? Is there going to be kind of a net movement? Right? I've got, I don't have 3 arms, but if I had a 3rd arm and, you know, people were pulling on my arms with the same force from those 3 directions, okay? Nobody's going to move. It's going to be like a tug of war that's a stalemate, okay? And so this is a nonpolar molecule because we're going to, there's no net, there's no uneven distribution of the charge, okay? The fluorines are kind of equally in, you know, in symmetrical directions, all pulling on those electrons, okay? So this is a nonpolar molecule. Because there's no net uneven charge distribution. All right, so let's look at another example, okay? One where you have a carbon and in the center. Okay, so this is example number 1. So example number 2 is we're going to have a carbon, and we're going to attach 4 things to it, okay? One's going to be a hydrogen, and the other 3 are going to be fluorines, okay? All right, so what type of geometry is this one going to have? Carbon attached to 4 things. It's going to be tetrahedral, right? So we've got, you know, sort of 3 things pointing sort of down on sides of a triangle, and then 1 thing pointing up. So this is tetrahedral geometry. All right, carbon has 2.5, hydrogen's 2.1, and our fluorine is 4 in terms of electronegativity, okay? All right, so these bonds are definitely polar, okay, towards the fluorine. So there's our bond dipoles, okay? And then if I look at my carbon-hydrogen bond, we typically think of carbon-hydrogen bonds as nonpolar because the electronegativity values are very close, okay? So they're 0.4 apart. That's really, really close. So we're going to call this a nonpolar bond, okay? So if we're looking at the bond dipoles, okay, we have a similar situation to the boron trifluoride where, okay, we've got 3 bond dipoles attached to our central atom. But in this case, instead of all being in the same plane, okay, they're all kind of pointing down, okay? So we've got 3 things that are sort of pointing down, and they're not going to offset each other, okay? And so what we're going to get is we're going to get a net dipole, okay, that is pointing, you know, somewhere down through the geometric center of those, and is bigger than any of those other 3. They're going to add up so that there's a net kind of dipole. So this one is a polar molecule. And again, it has to do with shape. If our boron trifluoride were a different shape, okay, if it weren't all in the same plane, then those, forces of the fluorines pulling on the electrons would not all be evened out and offsetting one another. Okay, so shape really matters, not just whether individual bonds are polar. Okay. All right, so this is just a fancy picture of what I drew by hand. Okay, so this is, again, nonpolar because all the forces, the dipoles offset. All right, and then, if we look, and then the other example that we just looked at, right, is, where we've got our 3 fluorines. Ignore that because that's inaccurate in terms of the size of the arrow, okay? But again, all these are going to add up so that you have a net force going down through the molecule, okay? All right, so let's do another example, okay? Here is a more complex structure, okay? And it actually has, okay, more than one central atom, right? So we've actually got kind of 3 positions in this molecule where we could determine a structure, okay? So if we can look at the carbon that's surrounded by hydrogens, okay? So if we look at this atom, okay, we could figure out what the geometry is around that. So what is the geometry around that particular carbon atom? What do we have? We've got a carbon attached to 1, 2, 3, 4 things, no lone pairs, okay? So our geometry around that is going to be tetrahedral, right? All right, so now, if we consider whether we have any net dipole around there, well, we've got carbon attached to 3 hydrogens and another carbon atom, okay, all of which have either the same or very similar electronegativity, okay? So this portion of the molecule, okay, that group right there, okay, we would consider nonpolar, okay? All right, so now let's look at the next carbon right here, okay? All right, so that carbon, okay, let's talk about the geometry at that carbon, okay? So this one right here. So what's the geometry going to be around that? So first of all, so we have our central atom is the carbon. How many things do we have attached to it? 1, 2, 3, or 4? How many say 3? How many say 4? All right, the 3s have it because remember that double bonds are considered as one thing when we're counting, okay? So this has 3 things around it, okay? So we've got a carbon with 3 structural pairs. So that's going to give us what kind of geometry? Look up in your chart. We got no lone pairs around it. Trigonal planar. All right, so what that means is we've got, our carbon, our oxygen, the other oxygen, all on in a triangle, okay, with this carbon, we'll move it a little bit, oops, in the center, okay? All right, so let's see, do we have any bond dipoles? Okay, so carbon and oxygen, oops, we go back here. Carbon's 2.5, oxygen's 3.5. That's a big enough difference to be significant, right? So we've got 2.5, 3.5, 2.5, 3.5. Okay, so in this case, we've got a couple of bond dipoles, right? So we've got one that's pointing towards this oxygen, okay? And then we've got one that's pointing towards that oxygen, okay? And we've got nothing on the other side, okay? So if we're looking at this triangle, we've got these things, and they are not, so trigonal planar geometry, this angle that's going to be between these two, okay, is 120 degrees. So they're not at 90-degree angles, okay? So there is going to be a net force, okay? All right, so when we look around this part of the molecule, okay, we would say that that's polar, okay? It's got a net dipole. Okay. And then the last portion of the molecule, we've got an oxygen as our molecular center, okay? The oxygen, this oxygen is very much like the oxygen in water, right? It's attached to two atoms, and it has two lone pairs, okay? So it's 4 structural pairs and 2 lone pairs. And what geometry does that give us? What shape is the water molecule? Yeah, it's bent. Excellent. Yep. So this is a bent geometry. And, you know, if we look here, yeah, there we go. It's bent, right? And so that's going to be, you know, somewhere between 100 and that angle is going to be somewhere between 104 and 109, you know, depending. Probably closer to 104. All right. Now let's figure out if these bonds here, and I'll draw it on the side over here on the right, do our bonds have dipoles? Well, we've got carbon and hydrogen, and we already figured that one out. It's got a dipole like that, okay? And then, carbon and oxygen. And then the hydrogen is 2.1, okay? So this is 2.1. That's also going to be polarized. And that's going to be that way, okay? All right, so this group, this group right here is also polar, okay? So what you see, the last thing that you see here, this right here, okay, is actually, so that picture was generated using WebMO, and that is the molecular dipole. So if you took, okay, the shape of the molecule and you added up all of these little individual dipoles that we figured out, okay, took into account the magnitude of the uneven distribution of charge, this is what you would get. So this is the overall molecular dipole. So acetic acid, does anybody know where you find acetic acid? Can anybody tell me what acetic acid smells like? Yeah, Ben. It is vinegar. Okay, so vinegar is a 4%, so vinegar you buy at the grocery store is a 4% solution of acetic acid. So this is vinegar. So if you like salt and vinegar potato chips, okay, what the vinegar flavor on those is actually sodium acetate. Okay, so it's the non-liquid, it's the ionic compound form of this molecule. And just because we're at the end of class and I feel like embarrassing my son in his absence, my son, who's a senior in college now, was a track athlete in high school, and he was obsessed with salt and vinegar potato chips, Pringles specifically, and he ate so many of them that he thought that, and he would always eat them like before and after track meets, and he thought that human sweat smelled like vinegar because his sweat smelled like vinegar because he ate so many salt and vinegar potato chips. So anyway, that's your not need to know fact about sodium acetate for the day. All right, so these two examples, okay, I want you to try on your own. I will record a separate little video that goes through the answer, okay, and then next class, we're going to kind of wrap up molecular polarity, and we will talk about what the nature of chemical bonds and hybridization and valence bond theory, okay? All right, have a good Wednesday afternoon, folks.